The next reaction that we're going to learn in chapter 22 is called the Claisen condensation. Claisen is a person, was a person. This reaction is really similar to the aldol reaction. So I'm going to start by drawing a generic Claisen reaction. This reaction is done with esters instead of aldehydes or ketones. And I am going to draw, an ester in this particular form. So there's a reason that I'm pointing this first R group, I'm pointing it down. It's going to make it kind of easier to see how this molecule works. And then also I do want to point out the R prime versus R. They could be the same alkyl group. They don't have to be different. This reaction uses a strong base and alkoxide that has an R group identical to that of the ester, the OR group. They have to be the same, and we'll talk about why it's the same. So that could be like OCH3, OME, OET, something like that. And then this is a step 2 H3O plus, which some of the problems on sapling call this acidic workup, which is just a pretty common way of saying step 2, add acid. The product of this reaction is a ketone / ester. And this is what it looks like. So I'm going to highlight that same OR prime. It's still there. So this is a reaction with two esters. One of the two esters that we have reacted here has stayed pretty much totally intact. And then the second ester has lost its OR group, but otherwise stayed pretty well intact. So before we look at the mechanism, let's talk about the OR prime as I've used it, in step 1. It's absolutely necessary. This has to match the OR of the ester. If it doesn't, you're going to get transesterification. So one of the things that will happen with an ester, like let's just use a specific ester, and let's use OET. One of the things that will happen with an ester is that OR group is super happy to swap. So if we have an OR group that is not the same as the OR group of the ester, when we make the product of the Claisen condensation reaction, there will be a couple different OR groups hanging off of that final product, which is not what we want to have happen. So we want to make sure that the OR groups match, so we avoid this situation. Let's take a look at the mechanism. Like I said, this is really similar to the aldol reaction. We are going to start with a pretty small ester just to make the reaction simple. And in our first step, we're going to use an alkoxide, an OR minus, and it has to match this guy right here. Otherwise, we'll get that transesterification. So that is an OCH3 methoxide. And the first thing that happens in this reaction is that strong base just grabs one of the alpha hydrogen of the ester. And so that gives us an enolate that looks like this. And just like in the aldol reaction, that enolate, I'm going to draw this over here, that enolate is going to react with a second ester that is unreacted. So this is a brand new, this is ester number 2, and that enolate is going to attack the ester's carbonyl carbon. So this is looking just like aldol reaction. And again, we want to be careful when we put these two molecules together. We want to be careful that we don't lose any carbons. So let's go ahead and number 1, 2, 3, 4, 5, 6. When I number for the Claisen reaction, I generally don't number the OR groups in the Claisen reaction. I leave them unnumbered. Also, as you know, I like to start by drawing the ester or the carbonyl compound that has been attacked. So that's the first one I'm going to draw. Those are carbons 4, 5, 6, and I drew that carbon-oxygen bond opened up with a lone pair on the oxygen, negative charge on the oxygen. And then in the attack process, we formed a bond between carbons 2 and 6. So there's carbon 2 that is now bonded to 6. Carbon 2 has carbon number 1 attached to it. Carbon 2 also has carbon number 3 attached. Carbon number 3 has a carbonyl group and the OCH3 group. So there's our first product. Now this is where the reaction is going to be different from an aldol reaction. In an aldol reaction, the next thing that we do is protonate the O-. But that is not what happens in Claisen condensation. In the Claisen condensation, the next step is that the oxygen, the negative charge, comes down and recreates that double bond, and it kicks off our OR group as a leaving group. And that's a very strong base, so it's kind of a weird leaving group, but that's what it does. So we're going to redraw this, and I'm not going to try to make it look pretty. I'm going to draw everything in the exact same position that it was in. I'm going to number those carbons 4, 5, 6, 1, 2, 3. So there we go. And now that I have it drawn like that, I'm going to feel okay with, I'm going to go ahead and try to redraw this and make it look nice. 4, 5, 6, 2, 1, 3, O methyl. 4, 5, 6, 2, 1, 3. So there it is. That looks pretty nice. Now you might be wondering, wait a minute, this reaction is supposed to have a step 2 H2O plus, but it kind of looks like it's done right now. So what's going on? Well, in this, if we back up to here, back up to this step right here, we spit out this leaving group, this OCH3 minus leaving group. I'm going to draw it down here. And that is a really strong base, methoxide. And so that methoxide is going to say, hey, do you got any alpha carbons or alpha hydrogens available for me? And on carbon number 2, I mean, we've got a few alpha hydrogens available because we've got some right here as well. But on carbon number 2, that alpha hydrogen is like extra alpha because it's sitting in the middle of 2 carbonyl groups. So it is really extra easy to be removed. And that strong base is going to grab it. And hey, maybe it grabs one of the ones off of carbon number 5 too. That's also a possibility. We don't really know. So we're going to get this looking, this guy right here. And that's not the product that we're trying to make. So this is why then we're going to come back in with an H3O plus, or even just water would probably work. And that is just simply to reprotonate at that site. And there's our product. So let's go to a worksheet and practice a couple of these reactions. So for this one, we're going to draw the mechanism and predict the product for the reaction. So I want to start by drawing in alpha hydrogen, and then I am going to use my alkoxide to grab that alpha hydrogen and pull it off the molecule and make an enolate. And the enolate is then going to react with ester number 2. It is going to attack the carbonyl carbon, open up the carbon-oxygen double bond, and give us, that's 1/2 of the molecule. The bond that we made, the carbon that we attacked with, was one of the ring carbons. That looks so weird. And that ring carbon, this ring carbon that attacked, not only was it part of the ring, but it also has an ester group attached to it. Now, I've just drawn some really disgusting bond angles there, but I don't care. I'm okay with that. And now I'm going to close my double bond up and get rid of the leaving group, and I'm going to redraw this, and I'm not concerned at all about trying to make it look nice. So we get this guy right here. That actually ended up looking pretty good. And for this particular reaction, remember, now we have this extra OCH3 running around that wants to deprotonate at this double E alpha site, but there aren't any hydrogens on that carbon. It's already got 4 bonds. So this reaction actually stops, and it doesn't need a step 2 H3O plus to go with it. Let's see if there's another one we can do. Oh, here's another one. So let's start by finding our alpha hydrogen, and we use our base to grab one of those alpha hydrogens and make an enolate right there. And then we will use that enolate to attack ester number 2 right there at its carbonyl carbon. And then let's draw what we've got. We've got that carbon-oxygen bond opened up, O-. We formed a bond to the last carbon of the chain. So this is the molecule that we've made. Let me put some numbers on those carbons so you can find all of them. 3, 4, 1, 2. And now we are going to close the carbon-oxygen double bond and get rid of that ethoxide leaving group. So that's going to give us this beautiful thing, which has alpha hydrogens on it. So that ethoxide that we kicked off as a leaving group is going to grab one of them and create an enolate like that. And technically, because nothing was listed down here as like a step 2 on this worksheet, this is technically where the reaction should end. But let's go ahead and give it some H3O plus just so we can practice that and form the actual product.